If you're a longtime gardener, well, you just might be a weather nerd. You may want to know what's happening, especially around your garden area and greenhouse, about many things, such as what's the high temperature? What's the low temperature? What about humidity, wind, soil temperature, rainfall, evapotranspiration rate, chill hours, growing degree days, heat index, UV radiation, and a lot more that can be affecting you and your plants. And your meteorological equipment right now may be as simple as a thermometer hanging outside your kitchen window, which may not be the best idea. We'll have more about that in a minute. Or it could be as complex as a really nifty weather station that set you back $1,000 or $2,000 that sends a myriad of data to your computer or phone or your in-house monitor. So if you're considering upgrading your backyard weather equipment, you also need to consider the placement of those various devices in your yard to get more accurate readings about what is really happening in your garden area, especially near your food crops. Today, we're going to get some answers to those questions from Daniel Swain. If that name sounds familiar, you may know him as the man behind weatherwest.com. He's a climate scientist focused on the dynamics and impacts of extreme events, including droughts, floods, storms, and wildfires. Daniel holds joint appointments as a climate scientist within the California Institute for Water Resources, within the University of California Ag and Natural Resources, the Institute of the Environment and Sustainability at UCLA, and he's a research fellow at the NSF National Center for Atmospheric Research. He's an alumnus of Davis and Stanford, and he completed postdoctoral work at UCLA. And again, his Weather West blog is excellent reading wherever you might be on social media, especially Twitter, Blue Sky, and YouTube, where he does presentations all the time about upcoming weather events. I've been a fan of his for years. Daniel, I'm finally glad to be able to talk to you in person. Welcome to the Garden Basics podcast.
Yes, thanks for the invitation to be here today. It's great to be on the show.
All right, let's talk about, I'd be curious about your own home weather setup. What's that like?
Yes. Well, today where I live, I actually am based physically in Boulder, Colorado these days because of that NCAR appointment, despite the primary one with University of California. So we don't own a home here, so I'm somewhat limited when I can personally install on this side of the Rocky Mountains. But back in California, I actually, back when I was in high school, believe it or not, installed a weather station on my parents' home in the North Bay, and that is something that I have maintained over the years on their roof. It's still there, it still gets maintained, and I'm still trying to use, to the best extent possible, best practices for meteorological station siting on that one.
I understand completely. I think when I bought my first large parcel of land, I got myself a Davis Instruments weather station, which was, at the time, one of the best you could buy. And that let me know a lot of things like wind direction, the high temperature, the low temperature, rainfall amounts, things like that. But it has gotten so much better over the last 20 or 30 years. And the data is much easier to comprehend as well because of either in-house monitors or the data is shot straight to your phone or your computer. It makes it a lot easier. But as they say in the computer world, garbage in, garbage out. So where you put that home station, no matter what kind it is, where you put it in your yard is very important, isn't it?
Oh, it's incredibly important. And this is actually something that I think is not always as obvious for a lot of folks as it might be to some meteorologists, although perhaps not even to all the meteorologists in the world who haven't worked a lot with actual physical instrumentation. And I think this is because, as you say, exactly where you put these devices and where they are relative to other things that might be in the immediate vicinity can make a huge difference into the numbers, the data you're actually seeing in front of you. And, as you mentioned, there's any number of different companies that manufacture weather instrumentation or packages of weather stations. Though, for my part, yeah, as was the case with you, the one I installed was indeed I think it was one of the Davis Vantage Pro stations, sort of the best consumer grade ones that they offered for many years. And it's still there. It's still chugging along. It's been recalibrated a couple times over 20 years at the factory, but it is still the same original hardware from 20 years ago, and it's still going strong with that careful maintenance. But the bigger issue, I think, is indeed where we put it. And the main reason for this is think about what you're actually measuring. For example, with something as simple as a thermometer, you're measuring technically the temperature of a small increment of air immediately surrounding that thermometer device, whatever the device is, if it's an electronic one or an alcohol-based thermometer or a digital one, whatever the particular mechanism is, you're measuring the immediate environment of that thermometer, right? So imagine two different scenarios: the same parcel of land, the same home, two thermometers within, say, 5 feet of each other. So there's not really a meaningful meteorological difference between the temperature across those 5 feet under normal circumstances. So the numbers should be the same. But imagine that one of those thermometers is just sitting out there in direct sunlight. You've mounted it in, on a pole above, say, a dirt field or a concrete or asphalt parking lot. That thermometer is going to read some awfully high values in the daytime and potentially some awfully low values in the nighttime. And that's because, of course, you have the sun, when it's sunny, is going to be directly shining on the thermometer, heating the thermometer itself because the sunlight is actually landing on the device itself. It's also going to be warmer because you've put it in an environment that is itself a bit artificially warmer than it could be. You've got your own local heat island effect if you're near that parking lot or that dirt field, because that sun is also heating the ground there more than it would if it were, say, grass or some other surface that weren't so solar radiation absorptive. So that thermometer is going to read a very high value. On a hot day, say, you might even get a value of, 120, 130 degrees on that thermometer. And does that tell you that the ambient air temperature is actually 120, 130 degrees? Well, yes and no, because assuming the thermometer is correct, it is reading correctly the temperature of something in that environment. But as we define the surface temperature, for example, whether we're talking about, the temperature at 2 meter height, so right around the top of my head, since I'm a little over 6 feet tall, that's kind of a standard meteorological temperature measurement that's used not just in science, but also for practical purposes and in agriculture and any number of applied purposes. That temperature is actually supposed to be a shade temperature. So the temperature of the air at about 6 feet off the ground where you don't have any direct sunlight. So if you're measuring a temperature, out in your dirt field or near the asphalt parking lot or in direct sun, even if you're over grass or something, what you're measuring is something different than the number that you're actually comparing to everyone else's numbers. So when you go to the Weather Service website and get a temperature forecast, or you look at observations from official Weather Service certified meteorological stations, the temperatures you're actually seeing are the 2 meter or the 6 foot height shade temperature. And if you've put your thermometer in one of those settings we were just talking about, what you're measuring is something else entirely. You're measuring essentially however hot a thermometer gets if you put it in direct sunlight over a very absorptive surface. Likewise, at night, the opposite can happen where those places get a bit colder than the 2 meter temperature correctly defined because they tend to radiate a lot of that energy back out to space if it's a clear sky, and so you're going to get a colder surface than one that has a little less variability day to night. So you might read a bit too hot or maybe a lot too hot in the daytime and potentially too cold at night. So your range is wider than the actual range of the temperature that we might define officially. And this is just for one specific simple atmospheric variable, right? We're just talking about the temperature. Things get even more complicated when we start talking about things like precipitation or wind, and then things get just really, really complicated. We can dig into the details, but I just wanted to offer, just how tricky it can be when we talk even about perhaps the simplest to measure atmospheric variable of temperature. And it's why, for example, when you look at the temperature on your car thermometer, when you're out on a hot sunny day, or the bank thermometer, you might see it on the side of the road. Those will read values that might seem kind of patently ridiculous. And the reason is those are often thermometers that are sitting there in the direct sunlight on someone's rooftop, or in the case of your car thermometer, right on the hood of your car. And think about how uncomfortable it would be if you tried to put your hand on the hood of a car on a hot, sunny day in the Central Valley. It's a lot hotter than the air, I'll tell you that.
For gardeners who may have only invested in maybe a remote thermometer that they can read indoors, and those units are widely available even at the big box stores, they sell for $20, $30, $40 or so. A practical application that they're looking for is, well, how cold is it under my citrus trees? Do I need to put a frost cloth over them? Do I need to protect them in some way from temperatures? And if all you have is a thermometer, as I used in the example outside your kitchen window, you're not getting an accurate temperature of what is happening out where your citrus trees are. So to protect that sensor, that thermometer sensor that is in your yard, would one strategy be to hang it 6 feet up in a citrus tree?
Well, I think, the key is it depends on what you're trying to measure. If you are trying to do, for example, frost or freeze protection, then it really does matter what the temperature is at the level of the plant that you're trying to protect. And, in the example, of a citrus tree, it could be very different. The height of where you're worried about, frost on the leaves or blossoms or fruit of a tree, as opposed to like a ground crop, or even something like vineyards, which are, often below head height at their highest point. You get what's known as a a microclimate, especially in the vertical direction. So I mentioned that going, 5 feet, 6 feet horizontally probably doesn't affect things very much most of the time. But going 5 feet vertically actually can make a pretty big difference, particularly at night when you have what's known as a temperature inversion, when temperatures actually increase with height instead of decreasing as they normally do in the lowest layer of the atmosphere. Sometimes that inversion can be noticeably important even within the first few feet off the surface of the ground. And that can matter if you're talking about, the top of a tomato plant, or the top of your grapevines versus the top of a fruiting, a fruit tree or a nut tree or something. So you sort of gotta measure exactly what you need to know in that case. How high are you actually measuring? Is it under the canopy, or is it on the top of the canopy? All of that can matter a lot for something as subtle as, making sure you're not falling below a particular temperature threshold. Might it be good enough if you only need to get within a couple of degrees for your purpose, in any of these locations? That might be fine. But if you really care which side of 32 degrees Fahrenheit the temperature is at a particular height, you probably got to measure it as close to that height and location as you possibly can, because you have these huge variations. In fact, a lot of the frost protection systems that are used in larger scale agricultural settings are really based on the knowledge that you do have these huge variations. Think about when people historically have used things as wild as helicopter downdraft, rotor downwash to sort of mix up the air, and during freeze events in orchards, or fans or windmills that mix the air. These aren't hundreds of, thousands of feet, tall towers that are doing the mixing. A lot of them are just a few tens of feet tall, and yet mixing the air from 30, 40 feet up to the ground can give you enough of a difference to prevent a freeze in a case where there's a huge difference between the very cold air right at ground level and the slightly less cold air 10, 20 feet up. So sometimes, frost protection is even leveraging the fact that these vertical microclimates exist. It's why you see vineyards, for example, on steep slopes on some of the hills. In any place where you grow wine grapes, part of that is because that cold air tends to kind of drain downhill into the valley below, or even the culverts and the rivulets below. It doesn't even need to be a big valley. So even just planting on a slope that's, 5, 10, 15 feet above the lowest point on the land gets you that extra degree or two of insulation. So long way of saying that you got to measure what you actually want to measure. And if it's something as sensitive as frost or freeze protection, you got to pinpoint exactly the height and the location where you're trying to protect against that condition.
So if I'm a gardener listening to this, it sounds like, well, if I'm really concerned about frost protection for my citrus trees, I'd want to hang that sensor a little bit lower in the tree, maybe only 2 feet off the ground, but in the shade of the canopy. But at night, that's not that big of a concern, the shade from the sun. But there sure is a big difference if all you have is a thermometer hanging on the wall of your house outside, and what may be happening 10, 20, 30, 40 feet or more away in your yard where that tree is growing. In my own amateur experimentation with that, I've seen as much as a 6 to an 8 degree difference where it's warmer on that thermometer near the house than it is actually out in the orchard.
Yeah, absolutely. I mean, I can believe it. Part of that, it's as we were talking about, there are genuine microclimates that can vary over that kind of distance, but it's also because your house, for example, might actually be warmer. Presumably, if it's a cold night, you have the heater on inside, and so some of that's going to bleed outside a little bit near your house if you have it hanging on a wall or an eave somewhere. Even a tree, for example, is going to exert perhaps a bit of a warming effect because if you have the thermometer under the leaf canopy, for example, you are actually that leaf canopy itself is going to be both absorbing and radiating some of its own infrared wavelength energy that is keeping things a little bit warmer than it would be if it were just out in a bare dirt or an asphalt field with nothing above you going out into the clear cold winter sky at night with less moisture around too. This is whether or not you've irrigated. Most
Mhm.
people who are farmers or gardeners know that once you put water in the soil, once you put water on the plants, once you irrigate, you kind of dampen the range of temperatures that you're going to experience. So you have less hot afternoons because more of the sun's energy is going into evaporating water or water transpiring through the plant's leaves. But at night, even if you have less transpiration, or evaporation, that water is still maintaining some thermal inertia in the tissues of the plant or in the soil because it has retained it from the daytime, and so it takes longer for damp soil, for example, to cool down than dry soil. So by having moisture in some places more than others, you're also going to actively, in some cases, create a temperature differential that's different than where you might be measuring at your house or out on the driveway or something else.
This is a tip we've passed along for years to people who have an orchard or citrus trees or whatever. It is basically test that sensor out in various locations to see where perhaps the coldest temperature might be. What's nice is there are some inexpensive units that are available that will have multiple sensors that you can hook up to one indoor monitor that can tell you the various temperatures at various points in your yard. And that's not a bad plan for any gardener before they plant anything, is figure out where most of the sun is if you really truly do need full sun, and also where the coldest parts is. So I always advise people, before you plant a garden, live with your house, live with your yard for a year and notice where the sun goes, where the shade goes, and where the temperatures go on a month-to-month basis before you do anything. I've noticed with people who buy, we'll say, the mid-range weather stations that have temperature, rainfall, and wind, a lot of these units, especially the wind part, is mounted on a rooftop. And I've often wondered, well, is that really accurate or not?
Well, when it comes to wind, the answer is unfortunately often going to be a pretty flat no. It's not accurate. And there's a number of reasons for this. One is that, first of all, commercial grade wind sensors are very finicky. There are different ways you can measure wind. Most familiar, is probably the spinning cup anemometer. So all wind gauges are anemometers, by the way. That's the technical term. But the spinning cup variety, it's exactly what it sounds like. It's usually three plastic or metal cups that are sort of rotating along a vertical axis, and the stronger the wind, the faster the cups rotate. They're sort of like scoops, mini ice cream scoops that sort of get caught by the wind and spin faster the stronger it gets. And that gets converted into a wind speed based on the number of rotations per unit time. The tricky part with these is that, they're highly susceptible to getting dirty or to becoming degraded over time. So anything from spider webs to dust to bird droppings to just good old rust will really affect that kind of sensor, really bias its wind speed kind of probably low. So you're estimating winds that are too low relative to real winds. And honestly, some of the ones, especially the lower to mid-range ones that come straight out of the manufacturers from the warehouse, they already aren't doing so well. So there is a challenge here where it's actually pretty difficult to measure wind correctly, even if you've sighted the instrumentation correctly, because of the inherent challenges with getting that kind of physical instrument to operate and be fully calibrated correctly. Sometimes at the higher end of the consumer grade, as you get into professional grade instrumentation, there are other forms of anemometers, of wind gauges, things like sonic anemometers, and those are becoming more common. Those are a little bit more resilient to that particular problem of friction, essentially, with the spinning cups, because there are no moving parts in a sonic anemometer. It's essentially the instrument is actively sending out sound waves between receivers, and it's measuring the distortion of those sound waves between two relatively nearby points. So there are no moving parts, and if it's calibrated correctly, that can be a decent option because it's a little more impervious to things like, you still got to clear the spider web off occasionally, but dust isn't going to affect it as much. Rust, and there's no spinning wheel to spinning ball bearing situation that you have to worry about. So that can be, an improved option, although it's usually more expensive. That's not what you're getting on your typical consumer grade station. But then there is the problem of sighting. Even the very best professional anemometer is going to be in error if you put it in the wrong place. And the wrong place, as you mentioned, it could be the roof line. Now, a lot of people put anemometers along the roof line because it's really just the most convenient spot. And I get it, sometimes you do the best that you can. But the problem with putting it along the roof line is that if you have a gusty wind, for example, and you're measuring it along the edge of a surface, think about what happens if you were standing up on the roof on a windy, stormy day. You probably don't want to stand too close to the edge because you get buffeted by all of these gusts and these eddies, these swirling, turbulent features. Because if you think about it, if the wind is hitting the side of your house, hopefully it's not going through your house unless you're inside of a tornado or something. Instead of going through your house, it's hitting the side of the house, and the air has mass and it has force, and it has to go somewhere. So where does it go? But it goes up. Once it hits the side of your house, it can't go down to the ground. It can't go through your house unless you have all the windows open, hopefully not. So it's got to go up. And so now all of a sudden you've artificially generated wind in a different direction than the ambient wind. You have upward force of that wind. And as it approaches the edge of your roof, now all of a sudden there's no barrier anymore. And so it's going to start to move back in the direction that it wanted to go originally. It's going to go back horizontally. But now you're going from an upward wind to a 90-degree change to a horizontal wind again. And that induces rotation or swirls or random turbulent eddies. So what I'm getting at is that if you have a anemometer mounted on the side of your house, whether or not it's a spinning cup or a sonic anemometer or something else, it's going to be really measuring all the turbulent eddies that your house produced rather than the ambient wind speed. And so you're going to be measuring, again, something other than what you actually want to measure. So ideally, what you do if you really want to know what the ambient winds are in a given location is you'd essentially mount your wind gauge, your anemometer, on a stick, on a post somewhere that's as far from vertical obstacles as you possibly can. So out, ideally, in an open field somewhere, and far enough above the surface that you're sort of getting away from the surface friction layer. So you want it to be, there's actually formula based on the height of the nearby objects or vegetation. You want it to sort of be above that. But in general, we often talk about 2-meter or 10-meter winds. 10 meters is kind of tall. That's like a 30-plus foot tower that is unrealistic for a lot of folks. But ideally, if you can mount it, in an open field or, even in an open lot, here there's less sensitivity than temperature, for example. So it's a little bit less of a problem if there's, a paved surface or a dirt surface or water nearby, because you're not trying to measure the temperature necessarily. You're trying to measure the wind. And here, what you're trying to optimize is the radius around the sensor where there's no tall vertical obstacles that could induce artificial turbulence or either artificially enhance or reduce the ambient wind speed. So here, unlike thermometers where you're trying to minimize the unwanted solar radiation exposure or the exposure to anomalously damp or heated or artificially cooled areas, here you're trying to avoid proximity to tall objects that could cause eddies or reduce the speed of that wind. So the challenge is if you have one unit where these sensors are integrated into the same physical object, these can be kind of goals that are in opposition to each other. But ideally, what you might have are sensors that you can physically separate and potentially even put them in different locations, because it might be that optimizing for your most accurate sighting for your wind gauge is different than optimizing for your most accurate sighting for your thermometer, for example.
And for those gardeners with a nice chunk of land where they can accomplish that, probably their first thing they'll do is go to Amazon and see what's available. And there's a lot of those sonic wind measurement devices available at fairly reasonable prices in the hundreds of dollars, not the thousands of dollars. And that sounds like a much more reliable way to measure the wind other than spinning cups.
Yeah, it certainly can be. It used to be the case that they were incredibly expensive, as you say, where the very cheapest ones were in the thousands. But I think this is another place where technology has the technological curve, mass adoption has made them a lot cheaper than they used to be. So they're still not trivially inexpensive, but they're also not nearly as financially out of reach as they once were, I think. So if I were buying a new one right now, I would probably do just that and look for a sonic anemometer, because they have, in general, you can imagine fewer moving parts, fewer problems.
Exactly. And again, on YouTube, it is Weather West, just as it is on all your social media outlets that you use, which is wonderful. And you have become America's meteorologist.
Well, there may be some colleagues on the Weather Channel who would disagree with that one. Although I do occasionally, I sort of am a recurring guest on a Weather Channel segment called The Weather Geeks, and it's kind of full circle for me in the sense that I was that weather geek. When we would be traveling and we get the cable television in motels all around the West on road trips, I'd turn on the Weather Channel and watch it. And now I get to have some conversations on air with some of those very same people that I was watching myself, 30 plus years ago. So it's kind of a fascinating experience to sort of be enmeshed in the weather world day to day in this moment in particular, and then to have the opportunity, through my new role with UCANR, which I'm really excited about, by the way, to expand the scope of these conversations even more.
And we're glad you're there. At Weather West is where you can find him on Blue Sky, on X or Twitter, as well as YouTube. He is now with the University of California Ag and Natural Resources as part of their California Institute for Water Resources. Daniel Swain, climate scientist. We've had a lot of great information today, and believe me, this is going to be very helpful for gardeners, especially when they start getting sun scald on their tomatoes and peppers this year.
Oh, yes. Well, hopefully it isn't too bad, but, it's always best to be prepared. And so hopefully I can help folks out in that regard.
Daniel Swain, thank you so much.
Thanks again for having me.